Okay, so in this example, we'll be using elementary matrices in a more contemporary way. So we're given a 3x4 matrix, and we're tasked with finding a sequence of elementary matrices that produces the row echelon form of the given matrix A. What does this mean exactly? It means we're going to be grabbing multiple elementary matrices, and we're going to multiply them with the coefficient matrix A, and hopefully it gives us matrix A, but in row echelon form. So let's look at our matrix, and where do we begin? Well, let's start with switching rows 1 and 2. And we'll leave row 3 as is. And we're going to write down the implications for that elementary matrix. So an identity matrix, this will be our first one. We only swap the first two rows. So it's going to look like this, with row 3 being the same. And now, our next step, well, what is our next step? And remember guys, the less elementary matrices, the easier it is for you guys to do the matrix multiplication, especially by hand. And I believe that we can multiply row 1 by -2, add it to row 3, and move the change to row 3. So we're leaving rows 1 and 2 the same, but we're multiplying row 1 by -2 and adding it to row 3, with the changing third row, as so. And it's going to look like this. Now what does that look like for our elementary matrix? Well, we know it's E2, and we multiplied the first row by -2, and we added it to row 3. And there we go. Okay. There's just one more thing we can do. Just one more thing. And I believe it can be even made simpler for our sake when it comes to multiplying it. We'll just grab the entirety of row 3, and we'll divide each entry within row 3 by 2. So it's just going to be 0, 0, 1, -2. And the operation is simply going to look like this. And we can apply the implication for the elementary matrix as such. Where the third row is just 0, 0, 1/2, and rows 1 and 2 will remain as is. And there you have it. We have a corner consisting of zeros, and this matrix is technically in row echelon form. Now, let's go back. What was the point of writing down those elementary matrices? Well, we're going to need those 3 elementary matrices, and we're going to multiply them by the coefficient matrix, and it's going to yield a new matrix, but with the given matrix in row echelon form. So let's say we have B, and we're going to multiply our operation is going to consist of multiplying 4 matrices. We'll start with our most recent elementary matrix to our oldest elementary matrix. So it's going to be E3 times E2 times E1 times the coefficient matrix A. And it's going to look like we already got our E values. Oops. So it's gonna be 1, 0, 0, 0, 1, 0, 0, 0, 1 half times the matrix 1, 0, negative 2, 0, 1, 0, 0, 0, 1 times our first elementary matrix 0, 1, 0, 1, 0, 0, 0, 0, 1. And I'm just going to duplicate our given coefficient matrix. And our first step, well, we gotta multiply all these out. And we're gonna multiply from left to right. So it's gonna be, we're gonna multiply E2 and E3. And that's gonna produce the matrix product of 1, 0, 0, 0, 1, 0, 0, 0, 1 half. You can always work this out in a calculator or by hand. I happen to did this problem in advance. And of course we are going to have quick correction, guys. So it turns out that E1 is just an identity matrix, and like in multiplication, multiplying any number by 1 doesn't change anything. So we're really just concerned with E2 times E3 times A. My bad for the mix-up, guys. So therefore, we're concerned with 3 terms that we gotta look out for. And now we just have to multiply E3 times E2. And therefore, we get a matrix product of 1, 0, 0 in the first row, 0, 1, 0 in the second row, and 0, 0, 1 half in the third row, times our coefficient matrix. And from here, what are the dimensions for this matrix multiplication? I think it's gonna be, let's see here, it's a 3 by 3 and a 3 by 4. It's gonna be a 3 by 4 matrix, so that helps. And if you run it through a calculator, you should have the matrix A, but it is gonna be in row echelon form. And there we go. So we have our coefficient matrix A and our objective matrix, which is B, the one we're looking for. And as a result, our 2 matrices A and B end up being row equivalent, because B was obtained by performing a sequence of row operations on A. That is, B is equal to this operation right here. Now, for matrix to possess row equivalence, A and B must be n by n matrices. And a matrix is row equivalent to another given matrix when there exists a finite number of elementary matrices, such that B is equal to the latest elementary matrix, the newest one, times the one before that, times those that came before it, and ultimately stops at the coefficient matrix.